Okay. So, last time we were looking at this existential elimination theorem. So, I have sort of changed the proof a bit. Okay, there were some bugs that I realized in my original version. They are very subtle bugs. But essentially the proof in its essence was correct, but but the whole point is this. You start with a proof tree which uses there exists elimination, and let us assume that there are some k applications of there exists elimination, then these k applications need not be on the in the leaves of the proof tree. That's the first thing. So, what you need to do is you need to identify an order of the applications based on the level in the proof tree. So, that you start off by eliminating the ones closest to the leaves, and once you eliminated all those ones that are closest to the leaves, you essentially you get different proof trees, because you will now add those things as assumptions. So, so essentially what we are saying is you start from the highest level of the tree, and there is some first application of there exists elimination, right. So, let us say that is a subtree T1, which, and if it is an application of there exists elimination, then it is a subtree T1 rooted at a formula like there exists y1 psi 1. Okay. And because of which, when you applied there exists elimination, you got this first constant A1, right. Now, it is clear that this tree T1 does not have any application of there exists elimination, right. So, now when you add A1 for y1 psi 1 to the set of assumptions, you remove this entire tree T1, but you retain this essentially this node with the assumption that A1 for y1 psi 1 is an extra assumption. Yeah. So, then that becomes a leaf of essentially a modified tree. Then on this modified tree, you look for essentially the second highest occurrence of there exists elimination and remove it, replace it, and add this an extra assumption A2 for y2 psi 1. Then look at the modified tree and then look at the highest, and so on. So, there is an order which there is a total order which you can impose, starting based on the levels, starting from the leaves and proceeding towards the root of the tree. So, each of these trees T1, T2, each tree Ti that you eliminate actually is of a modified tree of the original proof. Yeah. So, this claim here essentially says that for each I there are k applications of the rule in the original proof. For each I there exist proof trees T1 prime, this should be Ti prime, okay, gamma with constants A1 to Ai minus 1 replacing y1 to yi minus 1 proves there exists yi psi I, and this proof tree does not have any application of there exists elimination, right. And the act of removing these subtrees and therefore getting modified proof trees means that, so all these proof trees Ti primes are completely free from any application of the rule there exists elimination, and the modified original proof tree with each modification at the ith stage you get a proof tree Ti. t superscript I, which has these I extra assumptions and which proves phi, and of course, there are k minus I applications of there exists elimination in this proof tree, right. That is, so this claim is, so this claim is important. In my original proof the other day, I actually assumed that all these applications could be taken at the leaves, but that is not true, because if I had existential quantifiers deeply nested inside the formulae, then I will have to extract out all the root nodes and go through several steps before I eliminate them. So this is the modification. So essentially this claim can be proven, and it goes into several. So there it ends, and after that essentially we use the fact that each of those T i's did not use their exists elimination in order to apply this modus ponens. So here I had written something which was wrong. So by claim 1 we know that there exists a proof of this a1 to a k minus 1 psi k minus 1 proves there exists y k psi k. We know that there is a proof of this which is completely free of any application of this rule, and you also have obtained through the last step and deduction theorem, you have applied you obtained this, and therefore you can now apply the rule MP, and you can get this result. And now with this new tree, proof tree, now this proof tree you can now start eliminating a k minus 1, and you will get a new proof tree, and so on and so forth till you have eliminated all of them. Okay. So this is, oh, by the way, I have also added a large number of exercises which you should look at. Some of them you may have to submit. Yeah. Okay. So now what it means is that, so there are so we have got existential elimination and we have got existential introduction. So essentially what we have is a full natural deduction proof system. That is it. Yeah. There ends the matter. As far as natural deduction is concerned, there ends the matter. Yeah. Okay. So you take this for all introduction, and there exists introduction and elimination rules, and add it to those propositional introduction and elimination rules, and you have a complete natural deduction system. Yeah. Except that the proofs in natural deduction now, because of their exists elimination, will look different from the proofs of the Hilbert style system. Whereas in the propositional case, we could actually prove every rule of the natural deduction system as derived from the Hilbert style system. Yeah. So now the proofs are different. Okay, there are a lot of, this is all for you to have fun. Okay, and so now let us get on to essentially the main thing now of moving quantifiers. So I am going to introduce some heavy notation. So I am going to use a vector like this to denote a sequence of quantifiers where these quantifiers could be either for all or there exists, yeah, any of them. And for any quantifier q, its dual I will denote with a bar, yeah, to show that it is clearly different from that, from q. So that is, so now what we have these fantastic equivalences which is homework for you to prove. Okay. Notice that there are some conditions you have to fulfill, these equivalences have to fulfill. Firstly, I am assuming that there is a variable z which is not free anywhere in any of these, and it is not any of these variables which are essentially going to be bound. Then for any vector of quantifiers followed by a not q prime, where q prime is one of the quantifiers, of course this is just like your De Morgan's law, then you invert the quantifier q prime. So you get q prime bar and you negate the body of this thing, and here you have q prime y phi or psi. Then what I can do is I can do an alpha conversion and replace that y by a z, and since z does not occur anywhere in all this, I can also move this quantifier prime z outside. Okay. So, this is and this is for OR, right, and similarly if the quantifier occurs on this side, then I can rename it and move this quantifier outside. Yeah. So, look at these logical equivalences as operating from left to right, right. So, what are we doing? We are moving quantifiers towards the left from the right, yeah, of any term. And of course, once you have proved it once you have done this for NOT and OR, it follows as a corollary that you can do similar things for the other operators. So, now I mean now that we have got our natural deduction system and so on, we can consider the full language, and so we will work with the full language. That is so, okay. So, here you have for AND, if you have q prime y, then I replace I alpha convert that q prime y phi to q prime z, z for y in phi, and since z is new, I can move this quantifier out. And similarly, in the case of this arrow, of course, in arrow it includes that particular thing, right. There is this inversion of the quantifier in the last, which we have already seen. We used it in our proof of there exists elimination theorem, right. Okay, so, this is the last one which corresponds to that, and actually it works for both quantifiers. The inversion of the quantifier happens for both quantifiers, and that is what this is supposed to. Okay. Once you have this, if you look at these 7 rules from left to right, that left hand side being replaced by the right hand side, then what happens in each case is that quantifiers are being moved from inside to the outer levels of the abstract syntax tree. I mean, they are being moved closer to the root of the syntax tree, right. So, these seven logical equivalences essentially take care of negation and OR and arrow. There is no similar logical equivalence for the biconditional, yeah, or no obvious logical equivalence for biconditional. Okay. Anyway, so what this means is that now we can define a sublanguage of the full language of first order predicate logic called the set of Prenex normal forms. So, this is so you take any quantifier free formula in the quantifier free subset of first order logic. So, that is chi belonging to QF1 of sigma, and then you can keep adding quantifiers to the left. Yeah. So, the formulas that are generated are such that there is a sequence of quantifiers and then there is a quantifier free body. That is, yeah. So, that is a Prenex normal form. So, a formula is in Prenex normal form if all the quantifiers occurring in the formula appear as a prefix, which is a vector of quantifiers, which is called the Prenex, and then there is a body that is quantifier free and consists of only atomic predicates and the propositional connectives, not, or, and so on. Okay. So, the Prenex normal form theorem says that for any first order logic formula, there is a logically equivalent formula in Prenex normal form, and the justification is essentially just that when I have the biconditional, I replace the biconditional by 2 conditionals, and after that, so I replace all biconditionals by the 2 conditionals given by this, and after that what I do is I use those 7 logical equivalences essentially to move the quantifiers. So, and I basically I use so one thing is, it's if I am moving quantifiers and forming a sequence of quantifiers, I want all the bound variables to be distinct, for example. So, which means that one has to use alpha conversion, but now we know that alpha conversion can be done, right. It was something we took for granted all our lives till we saw the proof of alpha conversion. So that you can get unique names for all bound and free variables. I mean, there is absolutely no clash of names. And then what you do is proceed by induction on the structure of that formula to move all the quantifiers by applying appropriate logical equivalences. Yeah. Okay, so then this would yield a formula psi in Prenex normal form, basically. Okay, right. What we also have from propositional logic is that every formula in propositional logic can be converted into a conjunctive normal form, right. So, basically one just uses the distributive laws to distribute or over and one uses negation and so on and so forth. And so, now what it means is, since we have a Prenex normal form, we can take the body is just a propositional form and use the conjunctive normal form algorithm to transform it into a Prenex conjunctive normal form. Okay, so one obvious corollary is that for any formula phi, there exists a logically equivalent formula psi in Prenex conjunctive normal form. Okay, now we are going into the interface between proof theory and model theory, right. Okay. One of the things that we did was we defined the semantics in terms of certain structures, right. So, let us okay, I do not since I do not have any link, I will not go back there. Okay. So, now what I can also do is, I can for any signature containing at least one constant symbol, basically this means a function of arity 0, right. That is all there is to it. A term is said to be ground if it is variable free, if there are no variables in the term. So, T naught of sigma is the set of ground terms, T sigma is the entire term algebra, right. I mean, loosely speaking, the T naught and T are all, they are not things in brown really, they are all things in violet color. Yeah, that is by my color coding conventions, right. So, a literal is a ground literal if it is an atomic predicate or a negation of an atomic predicate in which all the parameters are variable free. Yeah. So, a literal is as we did in the case of resolution in propositional logic, you have the notion of a positive and a negative literal. And we will now what we can say is, we can think of this T sigma itself as a carrier of a sigma algebra. So, as a domain of a sigma algebra, if T sigma itself is the domain of a sigma algebra, and of course, T sigma is closed under the functions of sigma, under all the operations in sigma. So, therefore, T sigma is a natural carrier for sigma itself. So, you consider the algebra, instead of considering an algebra as sigma comma A, you consider the algebra as sigma comma T sigma. Okay. And that is a Herbrand algebra. Yeah. So, we will call that H of sigma, right. So, in particular, so the important thing here to realize is that there should be at least one constant symbol, because what happens otherwise is that you are essentially applying functions on functions and functions and functions, and that can be infinite regress. So, if you want to have a basis somewhere, there has to be a constant symbol. Since you are not going outside for a model, you are looking for models within the language of terms itself. So, we do require some ground terms. If we did not have any constant, then there would not be any ground terms. There would only be terms with variables in them but there would be no ground terms. Yeah. Okay. So that is why this it is important to have at least one constant symbol. And okay, so it is quite reminiscent of whatever you have done about many of you must have done some things about freely generated groups. Okay. I mean, so it is essentially something like that. It is a free algebra generated from sigma itself. Yeah. So that basically what I am saying is there is no brown color anywhere, everywhere it is violet. The carrier set is violet in color, it is not in brown. Yeah. Okay. So this is called a Herbrand algebra, and it is essentially the domain of the algebra are just the set of all ground terms. And if there was no constant symbol, then this set of ground terms would be empty. That is the problem. Yeah. So you want it to be non-empty, so you have this. So you take a Herbrand algebra. So now what we can do is now of course we can talk of valuations. So a valuation now will be a function from the variables v to essentially ground terms of this algebra. Right. So so essentially what we are saying is, so I can define, if I can define an interpretation over h of sigma such that every function symbol f in the signature is interpreted as itself in h of sigma, right. And a valuation is simply a function which associates with each variable a ground term. So the only difference is that we are not associating anything with the predicate symbols. Yeah. Okay. Right. So at the moment we are leaving the predicate symbols alone. Okay. So now a Herbrand interpretation is just a Herbrand algebra. Here I have just a Herbrand algebra. This should be h of sigma, but often I will just, even the sigma is understood, I will not mention it. And then there is a valuation where for each variable x I have a term, a ground term, that is why it is purple, it is violet in color, s x in t naught of sigma. Yeah. And so for any term t which has variables x 1 to x k, if you were to evaluate this term in this valuation V h, then what you are essentially going to get is a substitution, is a pure syntactic substitution. So every occurrence of the variable x 1 will be replaced by the term s x 1. Yeah. Of course, s x 1 itself, of course, the s x 1 in this case would be a ground term. So it would be variable free. Yeah. So what this means is that every valuation essentially defines a substitution. One of the things I did when we did all those coincidence lemmas and so on and so forth was we showed how variations in valuations are equivalent to substitutions in a certain sense. But now when your valuations themselves are in the same set of terms, then everything collapses to just substitutions. The only thing here is not any arbitrary substitution, it is a substitution of ground terms for variables. Yeah. Okay. So valuations represent merely substitutions on terms. So we would say, so now we have still not actually interpreted the predicate symbols. A Herbrand model of a set phi of sigma formulae is merely a valuation. I mean, you can just associate it with a valuation V h, which makes every formula in phi true. Okay. And if it makes every formula in phi true, then you are not really interested in the entire set of if phi is an finite set of formulae, then it will anyway only have a finite set of free variables, right. and if it has only a finite set of free variables, then you only need to consider the valuation restricted to that finite set of free variables. So, which is essentially a substitution, because a substitution strictly speaking is a finite replacement of variables. It's an almost everywhere the identity function, right. That means you have an infinite set of variables, but what you are saying is there are only a finite subset of those variables which are being replaced by non-identical terms, right, which are not being replaced by themselves. So in the case of any valuation VH, essentially a Herbrand model of a set phi will be restricted to the substitution created by restricting this valuation to the free variables of phi. Okay. Now, supposing so let sigma be a signature, and let us consider a finite set of literals lambda 1 to lambda k. Yeah. So, these are ground literals. So, they are variable free, and so they are essentially atomic predicates on ground terms or negations of atomic predicates on ground terms. That is what they are. Okay. Then lambda I has a model, the big AND of lambda I has a model, by a model we are saying actually we are referring to a Herbrand model, but at the moment let us just look at it this way, our proof will actually construct a Herbrand model. Yeah. So, the big AND of lambda I has a model if and only if capital lambda does not contain a complementary pair. Yeah. And big AND of lambda I can never be logically valid. Yeah. And big OR of lambda I always has a model, and big OR of lambda I is logically valid if and only if it has a complementary pair, right. The whole point about all this is that in order to look for models for formulae, we do not need to go anywhere else. We could actually look within the term algebra itself by looking for Herbrand models. So, one of the important theorems which I may not do today, but I do not think I can do it today, but which we will use is so all this that we are doing is what leads us eventually to finding to logic programming basically. Let us look at it this way. If you have a logic program which has to do some computation, it essentially tries to find some model for the axioms you give it. Okay. Now, it can't no computational mechanism can deal with arbitrary mathematical theories to find models. So, it will have to look within itself, within the language of terms itself, in order to determine whether there is a model. And so, we require a theorem which says that there is a model in the external world if and only if there is a Herbrand model. If you have such a theorem, then what it means is that your computational mechanism needs to look only within itself. It does not have to look outside in the rest of the world. If your theorem is weaker, which says that if there is a Herbrand model, then there is also a model in the outside world, then it is not sufficient, because what it means is that there might be models in the outside world and you may never be able to find a model within this, right. Okay. So, this theorem is the first step towards moving towards essentially inward looking models. So, what are known as term models. So, these Herbrand models in first order logic are in the larger terminology of universal algebra, they would be called term models basically. In a certain sense, all our computations are dealing only with term models. So, you can think of them as terms, you can think of all your models of computation involving a machine, let us say, as essentially looking at that machine as a sigma algebra, where the sigma are all the operations that the machine can perform, and all the expressions that are dealt with are just the terms of that sigma algebra, right. So, this is a fairly powerful notion that which actually brings us to computation, and in fact, it brings us to the notion of computation from logic much later than people realized. I mean, it is only in the 60s that Robinson realized that this could be done, though people like Herbrand had actually proved these theorems in the 30s. Right. So, okay, let's prove this theorem. So, what do we have to do in order to so let's take this big conjunction of lambda i's, and if it does have a complementary pair, of course, there is no way it can have a model. I mean, it's already gone, right. So, let us assume it does not have a complementary pair. So, if it has a model, then it definitely cannot have a complementary pair. That is one thing. Yeah. So, let us assume that it does not contain a complementary pair. So, these lambda 1 to lambda k's, all of them are of the form, let us say, some p 1 of some purple ground terms, right, some p 1, some p 2, something maybe of some other terms, let us say u 1 to u n. Then maybe another one is maybe just p 1 itself, but with some different set of terms s 1 to s n. Yeah. So, this k could be a very large set. I mean, this k could be a very large number, lambda 1 to lambda k. So, all these lambdas are essentially these kinds of atomic formulae. So, it could for example have this. Yeah. Yeah. So, you have got a set of, in your sigma you have got a set of atomic predicate symbols with their arities, and you take various, and you take your lambda 1 to lambda k is constructed out of various ground terms. I mean, this is somewhere ground literals, right. So, they are all ground terms, which means they are completely variable free. Now, what you are saying is, and you are saying that there is no complementary pair. Note that if S 1 to S n are different from T 1 to T n, clearly this is not a complementary pair, because we have moved away from propositions to parameterized propositions. So, a complementary pair, these two would be complementary pairs only if they looked exactly identical, if they had identical abstract syntax trees, or rather this was an identical abstract subtree of this formula, right. Otherwise, they would not be complementary pairs. So, complementary pairs, the parameters should also match. Okay. So, then what do? We essentially have to create a model, and we are going to create the model as a Herbrand model. So, we are going to create a model within terms itself. So, our model is going to be entirely purple in color, violet in color, right. So, what we do is we take this tuple, supposing this is one of the lambda i's, then our model actually should define a relation, right. P1H, let us say, should actually be a subset of T naught sigma the whole raised to n, right. If for P1 it has to have this, it has to have this kind of structure, right, and we have to take the ground terms. So, what we do is we define the interpretation of P1 as essentially this set of all these tuples T1 to Tn such that P1 of T1 to Tn belongs to capital lambda. Okay. So, you take all these n tuples of terms where, so for example, you could also have some other term, right. You could also have another term with the same atomic predicate also occurring in positive form, which is some term of let us say R1 to Rn, right, where R1 and to Rn are terms, right. So, essentially what we are saying is from this set our interpretation of P1 will contain these two tuples R1 to Rn and T1 to Tn, but it is not going to contain the tuple S1 to Sn, right. That is important to realize that. So, for any formula that, so essentially any literal that occurs positively in lambda, its parameters which are ground literals, which are ground terms, they are included in the interpretation of that, in the meaning of that relation of that the relation corresponding to that atomic predicate. So, this is how we construct. So, now this is a Herbrand model of this set lambda. You take any literal in this set, you can show that this is a lambda. So, you can, so this entire interpretation, this algebra is a model of that literal. So, that is essentially I am calling this H lambda satisfies lambda I, or H lambda is a model of lambda I for each lambda I. Okay. So, there are only two possibilities for lambda I. If lambda I occurs in positive form like this, then its parameters are there in the model, and so it is true. If lambda I occurs in a negative form or like this, then of course its parameters are not in this. So, therefore, by the semantics of the predicate, not P1 of that tuple is true. So, every literal lambda I is modeled by this H lambda. What is there in H lambda? The only thing new in H lambda is that H is already a Herbrand model. So, anyway the terms are your T naught sigma, right. There is no valuation now, because we are anyway talking about ground literals. So, it does not matter what valuation you have. The only thing you need to do is to interpret the predicate symbols, and so we interpret the predicate symbols like this. So, every lambda I is modeled by this H lambda defined essentially like this. So, the relation P H for each atomic predicate symbol P contains the tuple T1 to Tn only if P T1 to Tn is a formula, is a ground literal in lambda. That is it. Yeah. So, essentially you ignore all the negative literals, consider only the positive literals and interpret them as the tuples, as their parameters as being in the relation. That is it. Okay. So, So, if so this H lambda models every lambda I, therefore, it also models the big wedge, the big AND of this lambda i's. Right. One thing is clear, any such set of ground literals, their big AND can never be logically valid. What is logical validity? Logical validity means it should hold for all models, for all interpretations. Yeah. But now, how many there are an uncountable number of interpretations outside. So, the only way is to look for a model within the Herbrand algebra, look for some interpretation within the Herbrand algebra, so that it does not model it, and then you have found a model for which you have found an interpretation for which the big AND is not true, and therefore, big AND is not valid. That is okay. I can take any literal, there is a model for the complement of the literal. Yeah, I can take that singleton set and there is a model for it. So, and now, so that interpretation is clearly not a model of this big AND of lambda I, and therefore, big AND of lambda I cannot be valid, cannot be logically valid, right. Okay. Big OR of lambda I has a model, because I can take any singleton set lambda I and just create a model for it. Yeah. In particular, by the way, in particular, if this lambda I that I chose was a negative literal, then essentially I can restrict my interpretation to the empty relation, right, and then I have obtained a model for it, right. So, I need to look only inward into the term algebra in order to look for models, right, and this any big OR is always is valid if and only if, well, if and only if the big AND of the complements has no model, if and only if the complement, this set contains a complementary pair, if and this set lambda bar contains a complementary pair if and only if lambda contains a complementary pair, right. So, this is the first step towards looking inward for models and thereby restricting your quest for models of sets of formulae in some tractable fashion. You just stay within your term algebra and do not go outside it. So, basically what we have to prove, which I am not going to do today, which I will do next time, is really that it is sufficient to look inside your term algebra, and it is not necessary to go outside. After that we will do some more model theory, where we will talk about countable and uncountable models and so on and so forth, but essentially if it is sufficient to look inside your term algebra for models, that means there is a model in the outside world if and only if there is a model in your term algebra. Supposing that is true, then what it means is it gives you a very amazing consequence, that your term algebra anyway has only a countable number of terms, which means that any first order theory which has a model should be having a countable model, should be having an at most countable model. So, the question of first order theories or sets of first order formulae which do not have countable models and have only uncountable models, that is a question that gets answered also by this, by Herbrand's theorem, right. So, we will look at all these things, and so you can see that this notion of countable models is a direct extension of compactness, right. In the case of compactness, it was for a countable set finite subsets. Here, for even for uncountable models, you are saying that you do not need to look for uncountable models, you look for just countable models, that is sufficient. Okay. Finite models are not always guaranteed, but but if every subset is finite, then you still have a countable number of finite subsets for a countable set, right. So, that may not be guaranteed. So, so now what we are doing is we are progressing out of proof theory gradually into model theory, and then we will get into first order theories like of numbers and so on. We also have to prove completeness, and we have to prove undecidability of. So there are some important things, but let's go through Herbrand models, and which essentially forms the basis of all logic programming actually, and then we will proceed. So I will stop here at this point.